here, and last time we got into some specific sort of orders of reactions. We talked about first order, second order, and zero order reactions. Remember that each of these have sort of specific rate constant sort of units, right? So for first order, 1/2 or reciprocal seconds. Again, as we talked about, pretty much 1 over some unit of time is pretty much the unit that you look for. It does not have to be seconds. Second order, 1/molar seconds is typically the units that we see for second order K. And zero order, because it's zero order, it will typically have the same sort of units as the rate constant, or the rate actually. And in this case, there's also some integrated rate laws. So we got like the natural log of A. Whoops, not that. Natural log of A is equal to natural log of A naught. Minus KT. We also have for second order 1/A is equal to 1/A naught plus KT. And lastly, here we have A is equal to A naught minus K2. Remember, these are basically our kind of concentration versus time dependency equations. They also will they also will give us really these graphs that we sort of look at, so we could rearrange these in a form of y is equal to mx plus b. For example, natural log of A is equal to minus kt plus the natural log of A naught. And again, that is basically what goes on the y, which is our natural log of A. And on the x here, as you can see, is our time. And this will yield us, again, in this case, a straight line where the slope is equal to minus k. Again, we have a negative slope in line, which will give us a positive value for the rate constant. Same thing here. We can rearrange this guy, same deal. Kt plus 1/A naught. And again, that's going to give us on the y 1/A and time. This again will give us, though, a positively sloping line. And lastly, if we rearrange this one in that sort of form, we end up with this equation here. And again, that gives us the concentration of A versus time. Again, a linear relationship, and will give us a slope that's equal to negative K. Now, we do have some half-life sort of formulas that go with this. So the half-life, which is the time it takes for half of whatever you got with to basically go away. For first order, it's going to be the natural log of 2, which is 0.693 divided by K. For our zero order, we're going to go concentration. Initial concentration times 2K is the half-life. And again, as you talked about last time, it is affected obviously by the initial concentration, and 1 over the initial concentration times K there will equal our half-life there for our second, or also affected by the initial concentration as well. So these are the important parts that you can get from each of these. And really, the units of the rate constant are really important because, like I mentioned before, they very often will not tell you sort of the order of the reaction. So they'll maybe just give you the rate constant, and based on the units, you need to know which one to choose. A couple other things we talked about, did you want to be careful with as you are kind of going through these equations, is the unit of time for both of these. Again, you want to make sure that unit of time is the same in each so that you don't have obviously one, say, in minutes, one in seconds, or something like that. And the other thing that's very common as well is sometimes you will have to use sort of the half-life equation and this equation sort of together. And that would be a situation where maybe they give you the half-life, but they do not give you K. So a lot of times you'd be solving for K, and then kind of putting it into that equation. And that's a very common sort of process. Questions on any there we talked about last time. All right, so I think we did that last example. Why don't we try this one here? How many minutes would it take for the concentration of A to go from 1.25 molar to 0.433 molar if it is zero order and has a half-life of about 22 hours, I guess is what I scribbled on there. Yeah. So see what you come up with on that. Okay, let's take a look. So obviously here they have to tell us it's zero order because we have no area information to know that. So we'll do our zero order reactions here and see our formulas. And we do have a half-life mentioned. So natural log of A to K there. So in this case, we obviously have our initial concentration of 1.25. We got our final concentration 0.433. And we have a half-life here of 22 hours. And we're looking for the time, which is this guy. So we're looking for that. We do have this, we do have this. So we are missing the rate constant in this case, and that's where, again, the half-life equation will come into play since I have the half-life. Obviously, in this case, I have the initial, so we can solve for K in this case. Now, because we want perhaps the final answer in minutes, I'm going to actually convert this into minutes up front, just so I'm in the right units at the end. If you don't do that, then obviously at the end, you need to do a conversion to get it to minutes. Because if you leave it in hours, you'll be in hours when you solve for time. So we got 22 hours. What do they say there? 1 hour, 60 minutes, I hope. So we'll go 22 times 60, 1320 minutes. We're going to rearrange here and solve for K. Basically, what ends up happening is these two guys switch places. You're going to multiply K to both sides and divide by the half-life. And that will give us that K is equal to A naught divided by 2 times the half-life here. So putting in there our initial concentration, 1.25 molar, our 2 and our half-life here of 1320 minutes. Obviously, if you left it in hours, you will have a different number than what I'm going to get right here. But in the end, it all should come out the same, hopefully. 2 times 1320 there. And that's going to give me here 0.000473449, we'll call it. And we will end up with molar minutes in this case, as my unit on top is minutes and bottom there is, I'm sorry, molarity on top and minutes on the bottom. And that's now going to give me really the missing piece that I need here. So pop in my numbers in there. We're going to go 0.433 equals 1.25 minus our rate constant we just found there. I didn't do too much rounding, obviously, here. Molar minutes. And then we have our time. And if we do all that here, I'm going to take 0.433 minus 1.25. And at that point, I'm then going to divide what I got on the other side over. So I'm going to take this guy and divide that over to this side. And if I do 0.000, actually, I'll just do this. There's that number right there. Looks like I will end up with around 1726 minutes in this case. The molarities cancel because this is molarity, right? On both sides. And when we divide, the molarities will cancel and bring the minutes to the top. Yeah, and that's how we get to our minutes. Any questions on that one there? So again, sometimes very commonly, if you feel like you're missing something to go into sort of the integrated rate law, but they do give you the half-life or something like that, that's probably what you're going to need to do is use the half-life equation to get the rate constant. Any questions on that? All right. So this is a nice little table, the summary of all the sort of formulas there. And what you need to know, obviously, you need to know pretty much this table, right? So you need to know what's here, and obviously the graphs that go with it, as we talked about. Again, if we have a linear graph of concentration versus time, that's going to give us a zero order. Natural log of A versus time, that's going to be first order, and 1 over A obviously would give us a zero second order sort of reaction. So the next thing we're going to actually talk about is energy and temperature and how it relates to sort of the rate of a reaction. And these are two energy diagrams. And on the left-hand side here, we have an exothermic diagram, as this is the reactants and this is the products. And basically, in this case, our reactants are higher in energy than our products. So the only way for our reactants to get down to our products is overall energy needs to be released in this process. Needs to be released here, our energy. And that obviously is basically your definition of an exothermic reaction. Opposite here on the right-hand side, our reactants are actually lower in energy than our products. And again, in order for our sort of reactants to get up there to products, energy has to be basically absorbed in this case. And that is an endothermic sort of process that's occurring. As you may know, thank you. As you may know, when a chemical reaction occurs, all that happens is we basically break bonds and make bonds. So as we proceed up this hill of energy, we're starting to break bonds, and we're also at the same time starting to make bonds as well. And this hill that the reactants have to climb to get to the other side is what is known as the activation energy, and it's sometimes abbreviated as E of A, is the minimum amount of energy that's required for a reaction to occur. So basically, kind of two things have to happen for products to form. The reactants need to actually come in contact with each other and collide with each other. They actually need to collide with each other in the appropriate location. They kind of hit each other in the wrong spot, and they're not going to get products to form. And in addition to kind of hitting each other in the right spot, they also need to hit each other with the right amount of energy to sort of kick off that reaction. And that's really the activation energy. And as you climb up this activation energy hill, we get to the very top here, and this is what is referred to as a transition state. And this little guy right here is what is sometimes referred to as which is at the very top of the hill here, a transition state complex, are sometimes referred to as the activated complex. And it is really a substance that has kind of partially made bonds and partially broken bonds. It's sort of a transition point to get to the products in that case. It also is, as you look up there, pretty much the highest point in the energy of this reaction. And what do we know about energy in terms of stability? If you have very high energy, am I really stable? No, right? In chemistry, things do not really like to be in high states of energy. That's usually a very unstable situation for them. They really want to be in lowest states of energy. So a lot of things that happen in chemistry is all about kind of lowering the overall energy of everything. And because of that, what would typically happen is this transition state complex is a pretty unstable sort of species, and it's usually very hard to isolate because it doesn't hang around a really long time because it's the highest point in energy, and relatively quickly it'll sort of drop down the hill to the other side. Same thing happens here on our endothermic. We're kind of working our way up the hill, and again, we're breaking bonds here, and we're making as well as we come up the hill. And the same thing, we get to the top, which is our transition state here. And again, we'll come down the hill relatively quickly. The activation energy hill, if you think about it, is really a major barrier to, for example, how fast the reaction will occur or how slow the reaction may occur as well. You have a relatively large activation energy, there probably is going to be less amount of reactant molecules that have enough energy to get up and over to the other side. And that usually would probably result in a much slower rate than if you had a much smaller activation hill, you might have a greater proportion of reactant molecules that could actually get up and over to the other side. We could actually see here the difference between endothermic and exothermic. And endothermic is a much bigger activation hill, right? And that's why overall energy is kind of put into that, right, to help that reaction along. If you want to think about it that way, they kind of net need to gain some energy along the way. Exothermic reaction has a negative delta H, right, for the reaction, a negative value for the change in enthalpy, which is the heat of a reaction. As you may know, or if you don't know, how you calculate that, right, is you take the difference between the energy of the reactants, and if I could draw a straight line, the energy of the products, and that is your delta H of your reaction in this case. And when you do calculate the delta H of a reaction, it is the delta H of your products minus the delta H of your reactants as you go from final state to initial state. So in a chemical reaction, right, the final state is the products, right? Initial state is the reactants where you started, and it's a state function, which is the only two things that are important, where you start and where you finish. So if you just think about it here, if we were to calculate delta H for this one on the left, our products are lower in energy, so you're going to take a smaller number minus a larger number, and that is what's going to give you that negative sign that's going to happen there for an endothermic reaction, exothermic reaction. For an endothermic reaction, we do the same here. We take the difference of the energy of those two. And once again, if we were to calculate our delta H of the reaction here, our products are actually a higher energy, so it's a larger number minus a smaller number. That yields you a positive value for the delta H of a reaction for an endothermic reaction. So if it's endothermic, you should end up with a positive value. Now, one of the ways, for example, that we can increase the rate of the reaction is with temperature, right? So if you just think about logically, if you increase the temperature, what you're doing is adding a lot more energy to the system. And that means that there will be a greater amount of reactants that will have enough energy to come up and over the hill. Like you're kind of help pushing them up and over hill, more people that maybe couldn't do it by themselves. Opposite is true as well. If you lower the temperature, right, what you're now going to have is a smaller amount of reactants that have enough energy to get up and over that hill to the other side. The end result of that is usually the rate of that reaction will slow down. So temperature plays a really big effect in helping people sort of get up and over that hill to the other side. Another thing that you could do is you could add a catalyst, for example, and you could add a catalyst. And again, as we talked about maybe earlier, a catalyst is not a reactant. It's not a product, and it does not get used up in the reaction. It is there really just to, in most cases, facilitate the reaction occurring faster. So it can find an alternative pathway for that particular reaction to happen, a more efficient energy pathway, if you will, for that reaction to happen. A lot of times, again, you see the catalyst written on top of the arrow. Could be a solid catalyst, could be an aqueous, like acid type catalyst, or something like platinum. And again, as I might have mentioned earlier, for example, if you had gas molecules just flying around to try to react with each other, it's going to take a certain amount of time, obviously, for them to come in contact with each other and hit each other with the right amount of energy. By adding something like a catalyst, maybe a solid catalyst, it may attract everybody to a more centralized location. And what that will allow is obviously greater chance for collisions to occur between reactive molecules than it would if they were just kind of flying around, hoping to run into each other. The end result of that is you probably have a greater amount of products being formed and the rate of the reaction will occur. So again, instead of having to walk up a giant mountain to get to the other side, maybe somebody finds a trap door, you can walk right through the mountain to get to the other side, right? Like in those cartoons. And that obviously is going to get you there a lot quicker than you had to go up and over to the other side. I know, the coyote and the roadrunner, right? It's all right. But essentially what's happening here is, for example, we had a reaction like this. What happens when you do have a catalyst involved, what it ultimately does by finding that alternative pathway is instead of having to climb this hill to get to the other side, it finds that alternative pathway and it's able to lower the activation energy hill. So maybe it only has to come up that high in a catalyzed sort of reaction. So it lowers ultimately the activation energy, and thus that's going to allow a greater amount of reactive molecules basically to get to their side. And the end result of that is, again, you should see the rate of your reaction increasing. Questions on that there? So there is an effect on temperature and the rate of the reaction as we've been talking about. And again, typically speaking, increase the temperature, rate of the reaction is going to occur faster, lower the temperature to opposites. This relationship is what is sometimes referred to as the Arrhenius equation or Arrhenius relationship. And we got a few things here. K is equal to A, E to the minus E of A, RT. This is one version of it. I would say in most cases, we don't use it too much this version. We actually go through it and natural log it. And but what some of these things are again are we'll see it again here in a second. This is our activation energy. That's our temperature in Kelvin. That is R. It is not the R that we use in the ideal gas law. It is the R that has energy associated with it, 8.314 joules per Kelvin per mole version. And A is the frequency factor, and the frequency factor is essentially the proportion of molecules that have enough energy basically to get to the other side. So that's sort of the frequency factor in a particular reaction. And obviously K is the rate constant. And as we talked about in general, the higher the rate constant value, the faster the reaction, the lower the sort of rate constant, kind of the slower the reaction will be in general. So again, we'll see another version of this equation that we use. Actually, two more versions of that equation. We'll see it shortly that we use in a more common way. As I was talking about, the energy barrier to all reactions is that activation energy. And again, when you get to the very peak of energy in that reaction coordinate, that again is the transition state. That's the highest point in energy in the reaction. And again, really what you got going on there in terms of species that are present are very, very unstable because again, they have partially made bonds, partially broken bonds. They're really in sort of a transitional state of breaking apart and giving us our products as opposed to our reactants that we started with. So here, for example, this sort of rearrangement could happen. What happens is as it goes up the hill, it's starting to break the bond between these two guys and starting to form some new bonds here as well. So we're breaking and making here. And then again, as it drops down, it sort of rearranges and makes a new carbon to carbon bond, different than the carbon to nitrogen bond it started with here, right? So again, kind of making and breaking as we go up the hill, we drop down the hill, and again, gets our new bond formation. So that equation that we just saw is probably more commonly used in one version in this form here. So if you kind of natural log through that equation up on top, we get this equation here, which is known as the Arrhenius equation. Also, the top one is as well. But again, this is very commonly the version of it that you see. What we do see here on this graph is the dependence of the temperature and the rate constant. So what we see here is at low temperatures, we have a low rate constant for that reaction. As we start to increase the temperature, we see a much larger rate constant, and thus would be a larger rate. Again, if you just think about the rate law, as we talked about in general, we got this going on, right? So this is the rate constant. So obviously here, if this increases in value, when you multiply by everything to the right, it's going to end up with a larger rate than if it decreases in value. And you multiply it to the right, you're going to have a smaller overall rate for that reaction. So again, temperature plays a direct relationship to that. And typically speaking, for a lot of reactions, if you increase it by 10 degrees Celsius, you oftentimes will see a doubling of the rate of the reaction. Now, why is this version of the Arrhenius equation used a lot? This is actually the version of the Arrhenius equation that is basically a graphical sort of version of it, and that is the form in a straight line. This is y is equal to mx plus b. So very common Arrhenius plot that you will see is on the y, we would have the natural log of k. On the x, we would graph 1 over the temperature in Kelvin. And this will give us a linear relationship and a straight line. And from that straight line, you could actually figure out the activation energy relatively easy, because it will basically be this here equal to the slope. You can use the slope there. Won't be equal to the slope. You can use the slope to find the activation energy. So I think we have that plot. So this is essentially an Arrhenius plot. Once again, y is equal to m. Let me just get that out. Mx plus b. So here again on the y, natural log of k, on the x, 1 over the temperature. And the slope here is going to equal minus E of A over R in this case. So if you do this, which you will do in one of the experiments coming up, and you make this plot, you can take the slope of the line and allow you to calculate the activation energy. Now, when you do calculate E of A, it should be a positive number, by the way. Yeah, so you should have a positive number. If you looked at those graphs we were looking at, it's positive, right? It's going upwards, right? So energy being put in, it's a positive sort of number that it should be. So that is why, by the way, the negative is here, because if I had the value for the slope of this line, would that be a positive or negative number? This line has a positive slope or negative slope? Negative, yeah. So this is going to be a negative number you're going to get. So this negative and this negative will turn your activation energy into a positive number, which it should be. You do also want to think about units as well, especially when we're using this. And we'll see another equation where it'll be really important as well. But this R, by the way, has units of joules, which means when you would do this and you solve for the activation energy, it'll actually be in joules. And a lot of times the activation energy is given in kilojoules. So you just got to be careful with some units and understand what units you're getting when you multiply, for example, the R to the other side. So this is super easy to figure out graphically. For example, the activation energy, essentially you just make a best fit line, take the slope of it and times it by the R value, and you'll basically have your activation energy. Any questions on that there? Yeah. Convert, what's that? You don't have to, if the question just asks, what is the activation energy, and that's all it sort of asks, you could give it in joules or kilojoules. I will say very commonly activation energy is given in units of kilojoules. And we'll see another version of this equation where you actually need to plug those numbers in. And sometimes people mess up on, leaving 1 in kilojoules and R's in joules, and then you'll be off by that factor of 1,000. So you just want to be conscious of the units as you kind of go through these equations here, that you're not off by like that factor of 1,000. Yeah. Yep. Now, as I mentioned before, it represents the frequency factor represents really that proportion of reactant molecules that have enough energy to get up and over to the other side. As we talked about, increasing the temperature will really increase the overall energy of the system and allow the reaction to occur faster. Now, when we talk about sort of, by the way, the other thing that we could also solve from this is the frequency factor graphically as well. In this case, the frequency factor, natural log of frequency factor, would equal b, which is the y-intercept, right, from your graph. So when you have that graph or that line given to you in the equation, you could also use it to solve for the frequency factor by doing a little bit of math there, taking the e of both sides. The units associated with the frequency factor are typically the units that are associated with the rate constant. So the rate constant units, for most part, if you have to solve for the frequency factor through a graph, is typically the same units as you have for the rate constant. Um, and typically, if you were going to use this in a graphical sense, you most likely will have a table given to you of K values and temperature values. And the K values, you would then need to go through all those K values before you make the graph and natural log them all, right? And the temperature values, if they happen to be given to you in Celsius, right, you need to convert it to Kelvin and take 1 over the Kelvin value and make your graph. I say this because in this chapter, there may be some homework problems where you might need to lay up a graph. It's the best way to kind of solve them. So you may have to make some graphs along the way. All right. So here again, it's just graphically what we see here, T1 versus T2. And in terms of T2 is a higher temperature than T1. And what that means is this is our activation energy where you got to get to. So under that first temperature, really only this amount of molecules have enough energy basically to get up and over that hill to the other side. By increasing the temperature, what we see is we now have basically that much of molecules, a much greater proportion of molecules by increasing that temperature now has enough energy to basically get up and over that energy barrier hill to get to the other side. And again, that is what we kind of see there and what we would expect. Now, as I mentioned before, this is a very common sort of equation that we use for plotting. So for example, if we look at this example here, O3 goes to O2. We want to determine the activation energy and the frequency factor. And this would be a typical sort of table maybe that you would be given in a problem or see in a problem. I would say more typical would be probably these might be even degrees Celsius. Sometimes they're given to you in. You got to do that Kelvin conversion. So if we wanted to make this graph, like I said before, what we would have to do is take 1 over this temperature and make sure it's in Kelvin there. And obviously for all these K values, we got to go natural log of K. And if you did that, you will get a plot such as this. And obviously you could get your added trend line and get your best fit line and your equation, and you get that equation. So why don't you here, using the information from this graph, calculate both the activation energy and the frequency factor. So what is the E of A based on this graph and the frequency factor? So why don't you give that a go? Okay, let's take a look at it. So once again, here we got sort of a graph that we made, obviously, from this table. We'd have to do some adjusting of those numbers to make this graph. We would do a best fit line, add a trend line, get our equation, and all that good stuff. And we know from the Arrhenius equation that basically E of A over R minus E of A over R is equal to the slope. And that's going to allow us to get, obviously, our activation energy here. So once again, our slope is going to equal minus E of A over R. Our slope from our graph here is that. So remember, we do need the negative there so that we do end up with a positive value for E of A, which is what it should be. Remember, our R is our one with our energy, joules per Kelvin per mole. So essentially, we're going to multiply this to the other side. We also want to remember we're also taking the negative with it as well. And that's going to get me something here, 1.12 to the 4 times 8.314. It's gonna get me an activation energy of 9311. We'll call it 7. These are joules. Once again, very commonly, I would say activation energy is typically given in kilojoules. So if we divided that by 1,000, we're looking at like 93.1 kilojoules as our activation energy in this case. There's any question on that there. Now, our frequency factor, which is really that proportion of molecules that have enough energy to kind of get up and over to the other side, can also be found graphically like this. And again, that is your y-intercept, right, is equal to the natural log of A in this case. And looking at our y-intercept, that's going to be our 26.8 number. So 26.8 equals the natural log of A. To get rid of that, we're going to E both sides, right? That just gets rid of the A on, or the natural log on that side. And that is going to get us here 26.8. And it is 4.36 times 10 to the 11. Usually a fairly large number as it's a proportion of molecules. So there's a lot of molecules happening in a reaction. As I mentioned earlier, typically speaking, the units of the frequency factor are the same units as you have for K. So you can go back to your table here and see that is basically 1 over molar seconds here are the units associated with that. Any questions on how to graphically sort of determine those things? You do need to be able to do that. Clearly on an exam, I'm not going to have you graph anything, but you may be given a graph, obviously, and need to use it to get some information from it. Yeah. But again, on homework problems, you may have to make some graphs and stuff like that. Yeah. Any questions on that? We'll just do the exam old school. Here's some graphing paper. Just start doing some graphing, all that good stuff. Now, who wants to do graphs? Nobody wants to do graphs. So if you have, for example, 2 points on that line that we basically just saw in that graphing version of it, you could actually just do more of a calculation base of the Arrhenius equation. It's sometimes referred to as a 2-point form of it. And basically what that means is you took 2 points off that line that we just graphed there. You wouldn't take the end points, technically speaking, it would be kind of the end points. But if you have more of a sort of mathematical way of doing that, you maybe have two K values given to you, two temperatures, or vice versa, or whatever it may be, or maybe know the activation energy and a temperature or anything like that. You could use this. Now, this equation here is the natural log of K2 over K1. So those are the rate constants at two different temperatures is equal to E of A, which is our activation energy over R, which is still, again, our 8.314 version of it. And this is what I was speaking about a second ago about the units. This is one where you're just going to plug and chug into this equation. And you may be solving for not the activation energy here, but you may be solving for maybe a K value or maybe a temperature value, and you're actually given the activation energy. And if you do so, you do need to remember, as I mentioned before, typically speaking, kilojoules is probably the units you're going to see for that. This is stuck with joules because of the constant. So again, you do need to do a conversion of, one of them to one unit or the other so that everything cancels out correctly. It doesn't really matter which way you go, but you do got to make sure you do that conversion. Otherwise, you're going to be off by that factor. Other super common error is, again, these temperatures need to be in Kelvin, not Celsius. Yeah, so they do need to be in Kelvin. Even again, if you're given a problem where they give you maybe one temperature in Celsius and ask for the other temperature in Celsius, when you go into this equation, you got to put them in Kelvin and then do the conversions afterwards. So we have natural log of K2 over K1 is equal to E of A over R times 1 over T1 minus 1 over T2. Now, I will say that this equation, there's probably, I would say, 3 different versions of it that you might see flying around, including a different version in our lab manual that we'll come across as well. And that's just because some cases they may distribute out. That's nothing writing there. They may distribute out, for example, the negative here, and that will put a negative on the outside, and that will also flip these guys around as well. And sometimes you'll even see a version of this equation where they kind of combo the denominator there and take like T1 times T2 and do something on the top as well. So there's like 3 different versions of this equation. So we're going to roll with this one, but if you find any legit one, they all should come out the same in terms of the answer. So don't be surprised if you kind of see that. So we're going to go with this one, which does not have the negative on the outside. K2 on the top, T1 on the bottom right there to start with. And again, just be aware of that in case you come across and go, that looks similar, but a little bit different. So why don't we try one here? The reaction of NO2 plus CO goes to CO2 and NO has a rate constant 2.57 at 701 Kelvin and 567 at 895. What is the activation energy in units of kilojoules? Why don't you give that a go, see what you come up with. we definitely don't want to do any graphing here. So we go natural log of K2 over K1. And that equals our E of A over R, 1 over our temperature there minus our other temperature there, both in Kelvin, which looks like they are. So we could call K1 here 2.57. And that goes with a T1 of 701. Again, if it wasn't converted to Kelvin, we definitely would need to do that. K2 here, 567. It really doesn't matter per se which one you call K1 or K2, as long as you keep the temperatures and the Ks that go together kind of together. And R is a constant, so we always have that. So here we would have the natural log of, looks like, what do I call there? 567 divided by 2.57 equals my E of A, which was what we're looking for in this case. Our R, 8.314 joules per Kelvin per mole. 1 over our initial temperature, 701, since it was already in Kelvin, and our second there, 895 Kelvin here. And cleaning up the, we'll go left-hand side here first. Remember, you do want to divide the 567 by the 2.757 first, and then take the natural log of it. And I'll go something like 5.39645 equals my E of A over 8.314. And maybe we'll clean up what we got going on in here. So 1 divided by 701 minus basically 1 divided by 895 in this case. Going to get us 0.000309215. However you want to do it, you got to multiply that to the other side, and you do need to divide that, I believe, the other side as well. And 5.39645. And we're going to divide it by my answer and multiply it by 8.314. Gonna get me here an E of A. And again, the units here will be joules based off of those units there. 145,097 joules are about 145 kilojoules. We divide by 1,000. Yeah. Any questions on that one? Yeah. Would you want us to write out? You don't necessarily have to. Are you talking about like the 0.003, all those? No, but you should write out. You could also use scientific notation if you wanted to, kind of shorthand it. I just kind of write out, keep an extra few digits and stuff because you really do want to, especially in this chapter and some of the other ones where we use kind of like the E and the natural log and stuff like that. If you do a little bit of rounding along the way, it does dramatically sometimes change the answer that you get at the end. So in terms of writing, if you want to write a few less numbers, but I would definitely recommend keeping a few more numbers on the calculation part of it. Otherwise, you might find yourself kind of really far off and stuff like that. So, yeah. But definitely not to give me every number or anything like that. Yeah. Other questions? Yeah. It does as long as the temperatures and stuff stay together. So, yeah. So typically speaking, like most people do what I just did, which is whichever one comes first, we'll call K1 in the problem, whichever one comes second. And it doesn't matter. You can flip them around as long as you keep the K value and the temperatures that are together as the ones or the twos. It'll work out the same. Yeah. Other questions? Got 'em. Then let's not do this. Maybe we'll do this one. Maybe I'll just make up one and see. Let's see. Got some numbers. Let's see. Maybe. All right. We want to know. What do I want here? All right. If we had a reaction had an activation energy, we'll go with 85 kilojoules. And at 20 degrees Celsius had a rate constant of We'll go 3.5 times 10 to the minus 3 reciprocal seconds. What would be the rate constant at 30 degrees Celsius? I think that's everything you need, I hope. Give that a go, see what you come up with. We'll hope my made up numbers work. We'll see. I guess we'll shortly find out, I suppose. Look, again, we're going to use our Arrhenius equation here. So do a little bit of that. E of A over R, 1 over T1 minus 1 over T2. So here, obviously, we have the activation energy given to us. We have rate constant, let's call that K1 at 3.5 times 10 to the minus 3 reciprocal seconds. That's at a temperature of 20 degrees Celsius. We are looking for the other K value at a temperature of 30 degrees Celsius. So we got pretty much almost everything we need there. We do need to do some conversions, obviously, of our temperatures into Kelvin. So if we add 273 to it there, we got 293 Kelvin, and 30 plus 273, 303 Kelvin here. At that point, we should be pretty good. I'm going to go into this here, natural log of K2, which is what I'm looking for, over K1, 3.5 times 10 to the minus 3 reciprocal seconds, equals my E of A. This is going to be 85. I'm going to actually multiply it by 1,000. The reason I'm multiplying by 1,000 is that will convert it to joules. That way, when I divide it by the bottom there, which is in joules, I should be in good shape. Again, you do need to do some type of conversion. If you want to go kilojoules, that's fine for both of them. But you do need to make sure they are in the same units. Otherwise, you will be off by that factor. 1 over our temperature there that we converted to Kelvin, 293 minus 1 over 303 in this case. All right, so just kind of, actually, I'm just going to clean up everything on this side, I think. So we're going to go 1 divided by 293 minus 1 divided by 303. We're going to then multiply it by 85 times 1,000 and divide it by 8.314 there. So that should give me a natural log of K2 over 3.5 times 10 to the minus 3 reciprocal seconds equals 1.15159. Again, we're going to E both sides there. That's going to get rid of that. And that will get us that K2 over 3.5 times 10 to the minus 3, 1 over seconds, equals 3.163225. Going to multiply that now to the other side. And that will get us here. See how bad I did making up numbers. Not too bad, I think. 0.0111. The units here would be the same units, obviously, as the other rate constant here. First off, any questions on that there? Now, it does make sense, right? Because what happened with my temperature here as I went from my first temperature to my second, it increased, right? So we would expect that the rate constant would also increase, which it did. We went up by a 10-degree difference, right? And in a lot of cases, that's enough to double it. We almost tripled it here, but then again, we did see an increase in the rate constant or the rate of the reaction. Questions on that there? Questions on the Arrhenius equation? All right. So the last thing we're going to talk about in this chapter is what's known as reaction mechanisms. And reaction mechanisms are a way to basically describe how a reaction takes place. So one of the things that you may be familiar with is the idea, and you probably saw this when you did something like Hess's law, that not all reactions occur, for example, reactants to products, right, in one sort of step. They may occur in multiple individual reactions. So, for example, you may have like A plus B goes to C plus D, then like C plus D goes to E plus F. And if you add those together, anything on opposite sides of the arrow will cancel. or reduce. And that gives us our overall reaction of A plus B goes to E plus F. And as a result, for example, of these kind of individual steps that occur. And those individual steps that occur in a reaction mechanism, those are what are referred to as elementary steps or elementary reactions. So for example, if you look at this reaction here, and you do this reaction, during the process of this reaction, N2O2 is actually detected. But if we look in the overall reaction there is no N2O2 listed at all. It's not a reactant, it's not a product. So what that implies is that this reaction obviously does not occur in just like a one-step process, that it probably occurs in maybe multiple step processes. And a possible explanation of why we see that happen is these two reactions here. Maybe it occurs in this sort of process where the NOs come together to make that N2O2, which would explain why we detect it. And then that N2O2 gets used up by the end of the reaction and is not present, and it cancels out when you add them together, basically. And that is what is sometimes referred to as an intermediate. And an intermediate in a reaction mechanism is something that basically gets formed early on, but does get completely used up at the end of the reaction and is actually not present at the end of the reaction. So these elementary steps may form processes along the way, and these series of reaction steps may form sort of species that basically appear and then disappear by the end of the reaction, which again is why it's not part of the overall reaction that is essentially happening here. And that is the important thing, that it cannot be, for example, present in the overall reaction. Now, we sometimes describe these elementary steps based on what's known as the molecularity of the reaction. There's unimolecular reactions, which basically have one reactant molecule. There's bimolecular reactions, which have two, and termolecular, which has three. As we talked about earlier, if you just think about the reactions you probably have seen, you usually don't see, like, 4, 5, 6, 7 reactants at once reacting, right? So, 1, 2, possibly 3 are very common sort of ones that we see. So both of these would be bimolecular, as there are two reactant molecules in each of those steps that are happening on the left-hand side of the arrow there. So that brings us to rate laws for elementary steps. And if you remember earlier on when we were talking about sort of rate laws and getting the orders of the reactions, the one thing that we said that we don't do is we do not use the coefficients in the balanced equation as the orders. So the one place, though, that we actually do that in kinetics is when you're doing reaction mechanisms. So if you're doing reaction mechanisms and you have an elementary step, one of these kind of individual steps is going to lead you to the products being formed, you actually can write a rate law for each of the elementary steps that are present. So for example, here, we could say the rate is equal to K times A, and we would use the coefficient here as the order. For this one, we would say the rate's equal to K times A, rate to the 1, and B to the 1. Here, this is the same as 2A, right, goes to our products. So we could write a rate law for this elementary step of K is equal to A, again, to the second order. So this is the only place really in kinetics where you could use the coefficients as those orders. And if we did anything like we did previously, you shouldn't do that. But if you're doing something like a reaction mechanism and it's an elementary step, you can actually use those coefficients. So the idea of this is we're trying to figure out, and in a lot of cases is this reaction mechanism that they propose, is these series of steps, is it a plausible mechanism? Is it really, for lack of a better description, is this like a good mechanism or a bad mechanism? Will this lead you to the reaction we're looking at? So there's really two things in order for something to be a good mechanism or a plausible mechanism. And by the way, if something is a good mechanism or a plausible mechanism, it may not always be the way that reaction occurs. It's just a plausible sort of explanation of how it can occur. The two things that has to happen for it to be a good one is when you take all the elementary steps, so when you add up all the individual reactions, it needs to give you obviously the overall reaction you're looking for. So if you have a mechanism and you add up all the steps and you get an equation that is different than the reaction that you're looking for, it is definitely not a good mechanism, right? But if you add up all the steps and the equation you get at the end of that is the same equation that you're looking at in the problem, then it's possibly a good mechanism. The next thing, which is really important, is there will always be a step in the mechanism that is actually the slowest step. And that is what is known as the rate determining step. It is sometimes abbreviated as the RDS for the rate determining step. That is the slowest step in the mechanism. And because it is the slowest step in the mechanism, it is really the most important because it is the one that determines the rate law for the overall reaction. So because it kind of holds up the line, it is the one that determines how fast that reaction can take place. As again, it's kind of like if you're in the 15 items or less line, the guy's got 400 items in front of you. He is the rate determining step for you getting out of that line, right? Till he gets through, you're not going to get there, right? So there will always be a step. Now, one of the things that is important about the rate determining step is it should have a rate law that matches the one that was found experimentally. So very common in mechanism problems, they'll tell you, hey, experimentally, this rate law was this, and it was found to be this. And if this is a good mechanism, those two things has to happen. You add up all the steps and it equals the reaction you're looking for. And secondly, when you identify in that mechanism of all those steps, which one is the rate determining step, when you write the rate law for the rate determining step, it should have the exact same rate law as the one that was found experimentally. So those are the two things that has to happen for it to be kind of a good mechanism. And there's a few different types of mechanism problems that we'll talk about. One is like they give you a mechanism and they go, is this a good mechanism or a bad mechanism? And you have to kind of prove that it is a good or a bad mechanism. One is where they kind of tell you based on this, what would be the rate law based on this mechanism and what would be the rate determining step. So there are a few different sort of variations of mechanism type problems. So let's take a look at this one here. So for example, the experimental rate law for this reaction of NO2 and CO to produce NO and CO2 is the rate is equal to K NO2 squared. The reaction is believed to occur through these two steps. So let's start with the first one. We want to figure out the overall equation. So that's pretty straightforward. We are going to add these guys together. And anything on opposite sides of the arrow in different equations will cancel or reduce. So the NO3 will cancel. And we also have an NO2 here that we'll get rid of. And that's everything else at this point. So that will leave us an overall reaction of everybody on the left-hand side of the arrow stays there. And everybody on the right-hand side of the arrow stays there. And this is my overall reaction in this case. First off, any questions on that there? Now, the question is, what is the intermediate in this case, and what should be the intermediate in this case? The intermediate is what things are thing. It is NO3, yeah, it got canceled out. Is NO2 an intermediate? What do you think? NO2 is not an intermediate. Even though we reduced it down, it is still present there in the overall reaction. So even though you reduce it down, it is not considered an intermediate. Definition of intermediate is you make it early on, it gets completely wiped out by the time the reaction's over. It should not be present in the overall reaction. So for this particular reaction, only NO3 is the intermediate. Now, we have the basically experimentally found rate law given to us in the problem. Let's get rid of some of these crossouts here so we can see that. So this is the rate law that was found experimentally. So this is basically our experimentally found, our observed rate law. Now, because these are elementary steps, as we talked about, we can actually write a rate law for each of these individual steps by themselves here. So if we did it for our first step, the rate would equal K times NO2, and it would be squared because this is essentially 2NO2, right? And that is where the 2 comes from. We could write a rate law for the second step, which is the rate is equal to K times NO3 and CO. Now, by doing this and knowing the experimental rate law, we should know a couple of things that we could determine. The first thing is step 1 or step 2? Which one is actually the rate determining step? Which one is the slowest step? Which one? So in this case, the actual one that is the rate determining step, in order to know which one is the rate determining step, I'll say it should have the same rate law as the one that was found experimentally. So which step has the same rate law as the one that was found experimentally? Yeah, step 1 is actually the rate determining step here. And that is because it has a matching rate law than one that was found experimentally. So that means that in this case, step 1 is going to be the slowest step in the mechanism. It is really the one that's going to determine the overall rate of this reaction. So when we talk about the relative rates of step 1 versus step 1 should be slowest, and step 2 should be relatively much faster than step 1. Um, so this is one type of sort of mechanism problem where they kind of give you the mechanism, they give you the rate law, and they ask things like, what's the rate determining step, which one's the slow step and the fast step.